Hello everybody again, and welcome to the fourth lecture of this course on control of linear systems. So we start this class by just making a summary of what we have seen about stability and the criteria to assess it. And I please ask you to pay a special attention to this slide over here, this table, because you basically have the recipe to solve all of your stability assessment problems in this slide. So you might be confronted with two different kinds when trying to assess stability of a linear system. You might have a system like this one on the left hand side with one specified input, one specified output, and the given transfer function for which you have the expression, the formula, or for which you can easily compute the formula, which we call t, t of s. And then you might be asked whether this transfer function from c to z, as written here, is stable. So in this case you have basically two options. The first option is that t has a denominator which is simple or which is already factorized, and then it is very easy to look at the poles, compute the roots of the denominator, and look at the real parts of the poles. As we have seen, strictly negative real parts mean that the system is BIBO stable, input-output stable, let's say. You might have also the chance of use this criterion if you have a computer and the denominator is complicated. You just pass this denominator to the computer, ask to compute the poles, and look at the real part of the poles. If you do not have a computer and the denominator of t is not factorized, so it's not easy to find out which are the roots of this denominator, then you might want to use a root always criterion as a last resort. Another case where you might want to use the root always criterion is whether you might try to study the stability with respect to a parameter. In this case also you might want to use this criterion instead of trying all the values, all the possible values of the parameter, and compute the poles subsequently. If instead you have a situation like this one on the right hand side, which means a closed loop system, a feedback system, and you are asked whether the transfer function from c to y is stable, not d alone, not r alone, but c to y, for which you know the expression would be this one, you have the chance, you have the possibility, if both d and r do not feature strictly positive real pole, you can use what we call the Bode criterion, which basically means compute L, the loop transfer function, as the product of d times r. Pay attention, this is true whether you have only if you have a negative feedback over here. If you have a positive feedback, then the loop transfer function would be minus dr. Okay, but in the case you have a negative feedback, d times r, loop transfer function. Draw the Bode diagram or the Nichols-Black diagram. Apply the criterion, and then you can decide whether from c to y the system is stable, and not only from c to y, from c to epsilon, from c to m, from any input perturbation you might have everywhere. The closed loop has only stable transfer function or only unstable transfer function, which means if you assess the stability of one transfer function from a signal coming to outside to any signal inside the loop, then all of them are stable. If you cannot apply this Bode criterion because, for example, one of these functions has a pole that is not strictly positive real part, then the only solution you have is to compute the transfer function explicitly, for example, from c to y, this is the expression, then simplify this transfer function, and then once you got this one, just look at the possibilities of the left hand side. In general, if you have a feedback loop like this one, the Bode criterion, in case it can be applied, is the easiest and quickest way to sort out the answer. And it's also nice because it can be used for synthesis, for tuning the controller, which is what we are going to do in the last part of this class, of this course. Now we go to another aspect, which is something that comes after stability. So once you have assessed the stability of a transfer function or of a closed loop, let's say, you might want to assess performance, and typically performance can be divided into two categories: the accuracy and the speed. And in order to do this, typically we rely onto theorem, the final value theorem, which we already seen in the first class, which basically says that if you have a signal, the final value of the signal, if it exists, I stress, if it exists, the limit for t going to infinity of x t correspond to the limit of s going to 0 of s times its Laplace transform. Do not forget there is an s times. Okay, so basically this thing allows you to understand what will be the trend, the ultimate trend of a signal when you look at a certain given input to a system. Typically, for a closed loop, for a feedback system, as we have seen in the first class, what is the accuracy? The accuracy is basically the difference between the set point and the measurement. So basically, your system is accurate, your closed loop system, your control system is accurate if this error goes to 0 eventually. Okay, so we call this performance the static precision. If you have a step change in set point, so static precision means, imagine your set point is constant or piecewise constant, it changes from a certain value to another constant value, then will the error be 0 eventually for t going to infinity? We might also define a dynamic precision, and then which depends also on the kind of set point, for which the set point changes with following a specific curve, and then we would like to see how the error follows, if it can be 0 as well, or it can be or not. For example, imagine the set point is a ramp. Can the error go to 0 eventually or not? And going from the general picture to the more mathematically oriented abstraction, we can tune this image here into this one, which is the familiar scheme for the control system, for the feedback system, which we have seen in one of the previous classes, where we have a C, the set point, P, the disturbance, then we have this D2, which is probably the plant, the system that you want to control, this function R, which is the measurement transfer function, which models the sensors basically, and this D1 from the error to the plant, let's say, is typically the controller which we want to tune, which we want to design. So, speaking of accuracy, well, we have already seen this expression beforehand. Actually, we have seen the expression of y as a function of c and p, but we can also write the expression of epsilon as a function of c and p. How we compute them, remember, it is a closed loop system, closed loop function, so as usual in the numerator, direct line from the input to output. So if we look at from c to epsilon, there is nothing in between, so it's just a 1, and then at the denominator we have a negative feedback, so we have 1 plus L. L is the product of all the elements in the loop, so D1, D2, and R. For what concerns the effect of P over epsilon, then we have again direct transfer on the numerator. We have D2, then we have R, and then we go through a minus sign, so we have minus R D2, and the denominator is always the same. Now you understand why all transfer functions in the loop have all the same stability properties, because the stability depends on the poles and the poles depend on the denominator, and you might notice that the denominator is always the same for this function. So you have basically a part of the error which depends on the set point, the tracking error if you wish, and then a part which depends on the disturbance error due to the disturbance and perturbation, whatever. Now we can try to be a little bit general and try to see how these errors behave as a function of the input. So how does the error due to C depend on C? So this is the transfer function we've written just beforehand. which we can also summarize like this. So if this is the transfer function from c to epsilon, then basically the Laplace transform of epsilon due to a certain c, input c, will be this transfer function times c, basically this one. And then you can use, in general, the inverse Laplace transform in order to compute the exact value of epsilon over time. But you can also look at the final value by using the final value theorem. That's what we are going to do. So is the final value of the error going to 0 or not? That's what we are interested in. And we can take into account different kind of signal. Typically, the standard signal we look into are those listed here. So you might have a step kind of set point with a Laplace transform like this, or a ramp type, parabolic type, etc. Well, usually we stop here, we don't go further in the reality. So how do we do this? Then we already seen in the previous slide the value of the transfer function from c to epsilon, then multiply this transfer function times the Laplace transform of c, and you get the Laplace transform of epsilon. And it turns out that for this kind of set points, as we've seen before, just basically c naught divided a certain power of m, the steady state error depends on how many integrators there are in the loop transfer function. What it means, how many integrators there are in the loop? It means basically if you write L in the canonical form, as we have done before, so there are some zeros, there are some poles which are not in zero, and then you factorize all the poles and zeros which are in zeros in one term over here, this 1 over s to the power n naught, and basically n naught is the number of integrators in the loop. It doesn't matter actually here if they are in D1, in D2, or in R. Okay, so let's see what happens. So basically you can expand this function here and write it like this. So how do we compute the final value of the error? Well, we apply the final value theorem. So this is epsilon c, the Laplace transform of the error due to c. We replace c with the general expression that we've seen before. So remember, m equals 0, it is just a step, m equal 1, ramp, etc. We replace L with the general expression we've seen before, which puts, let's say, which stresses the presence of n naught poles in 0. Okay, then what we do, we can just factorize this term over here, and this Laplace transform of the error is equivalent to this one. We just multiply and divide the numerator, this part here, multiply numerator and denominator by s to the power n naught, so we are left with this thing here. And then basically one can simplify s here and s here according to m and n naught. So now we apply the final value theorem. So the limit for epsilon of c for t going to infinity is the limit for s going to 0 of the Laplace transform of epsilon of c times s. Do not forget times s, which basically yields this thing over here. This s simplifies with the s here, the plus 1 disappear, and you are left with this one. Now, computing this limit, pay attention to this part. This part over here, well, it's just the product of some terms over here, product of some terms over there. All the parts, if this is normalized with the 1 on the constant part, then s goes to 0, s goes to 0, no problem. This just goes to 1, and we are left with a k. And then you basically have s naught here going to 0 as well, and then you have this going to 0 and this going to 0. So now, according to which power you have here and which power you have here, you will either have a 0 on the numerator or a 0 at the denominator, which means that the limit will be infinity, or you might have a number if these two are the same. So basically the outcomes are these ones. If n naught is bigger than m, then you get a 0 over here and your limit is 0. So it means that if the number of integrators in the loop is bigger than m, then you get zero steady state error. If you have n0 equal m, so as many integrators in the loop as m, then you get some numbers, finite numbers. If the numbers of integrators in the loop is strictly smaller than m, then you get infinity. So let's translate these ones into some examples. This is just the simple expression that says it all, but translating it into examples. How many integrators you have in the loop? 0, 1, or 2. So if you have a step in the set point, which means m equal to 1, m equal to 1, m equal to 0, then, as we said before, n equal m equal to 0, you have this steady state error, as you can see here. If you have n0 greater than m, which is the case for 1 or 2 integrators in the loop, the limit will be 0. If you have a ramp, which means m equal to 1, and no integrators, then you are in the case of infinite steady state value. If you have one integrator for m equal 1, which is the ramp, then you have a number. If you have two integrators and two integrators and m equal 1, so for a ramp, then the final value is 0. So basically what this means, it means that if you want to follow a step and get exactly 0, you need at least one integrator. If you want to follow a ramp and want to follow it exactly, you need at least two integrators, etc., etc. This, of course, is if the closed loop is stable. In fact, you remember what I said, this limit here, this final value theorem, holds if and only if the limit exists, but this is, of course, subject to the fact that the closed loop is stable, otherwise it doesn't make sense at all. So when designing a controller, one should, of course, check beforehand the stability of the controller before setting the numbers when setting the numbers of integrators, in order to make sure the system is not unstable. Now let's look at the error due to disturbance. Again, assuming that the closed loop is stable, you can write the transfer function from p, the disturbance, to epsilon, as this, as we've seen before, which allows you to rewrite it in this manner just by factorizing this term over here as L, and D1 is left outside. So you can write it like this. So this means that basically the effect of the integrators in this transfer function for the final value is limited to the integrators which are present in D1. So we have to focus on the numbers of integrators in D1. So we call N1 the numbers of integrators in D1. So we write L as before, like this, and D1 will be something similar with S to the power N1 at the denominator. And by doing exactly the same computation as before, you can work out the limit, etc., etc., and basically you get that the limit of the error due to the disturbance goes to 0 if the numbers of integrators N1 in D1 is greater than m. You get a finite number if N1 equal m, and an infinite value if N1 is smaller than m, which means that, for example, if you have a step, let's look at here. If you have a step going in here and you want a 0 steady state error, you need to have an integrator over here in D1. If you have an integrator over here and no integrators here, then you will have a final value of a finite number. If you have a ramp over here, you will need two integrators in order to get 0 error. 0 error means epsilon equals 0, so c equal the measurement of the y, the measure m. Okay, so why we seen this, and what is the moral of the story? The moral of the story is that the precision of the control system, which is basically determined by tuning this D1, the static precision and dynamic precision for specific signals which might come in here or here, depends on the integrators in the loop, and namely in the integrators in L, so any element in the loop for C, and integrators in D1 for the disturbance coming into P. So basically this gives you a rule of thumb to tune your controller, because you know if you want to follow a certain kind of signal that you will have to put some integrators over here, always taking care of the stability. Now let's probably this doesn't tell you much at this time. It has probably been confusing, but now we see some examples and probably this issue will be clarified. So let's go to the examples. Again, you can try and do it yourself. The idea is to find out which is the final value of y as a function of a certain input in the set point and as a function of a certain input in the disturbance B. And of course the stability is a necessary condition before one can do this exercise, so also assessing the stability easily could be interesting before proceeding. And then how do you proceed? Well, basically for all of the examples over here, in order to compute the final value, the steady state value of the error or of y, you just need to compute the transfer function from either P to y or either C to y, write it down, then multiply this transfer function times the Laplace transform of the input that you consider, and then use the final value theorem to see which is the final value of it. So you can try and do it yourself and check the solution, or you can just wait a few seconds and look at the solution over here. In 3, 2, 1, there we go. So let's first consider from C to y. So let's write the transfer function from C to y. It is basically L divided by 1 plus L. So what was L over here? 0.5 over S plus 1 times 1 over S plus 1. So you basically get L equal to 0.5 divided by S plus 1 square. And before we continue, we can notice that this is basically the closed loop, a feedback loop with L of degree 2. So basically L goes from 0 to minus 180 degrees of phase. So it will never hit minus 180 degrees. So this system in closed loop is stable from C to Y. Because you remember the Bode criterion, if you never hit minus 180 degrees, it means that your closed loop is stable. If your L never hits minus 180 degrees, which this one does only asymptotically, so it never hits, then you don't need to worry about stability. So this function, this transfer function, is from C to Y stable. So there you go, and this is it. If you simplify it, you have this thing, and again you can also see it here that it is stable. If you remember, we said that one of the consequences of the Routh-Hurwitz criterion is that a second order denominator yields a stable system if all the coefficients are of the same sign, and here we have only positive coefficients, which means roots with negative real parts. So we are safe. This transfer function is stable and we can apply the final value theorem. So the output yc due to C will be transfer function times C, the Laplace transform of a unit step 1 over S, which will be this one. So final value theorem, limit of y of C for t going to infinity equal limit for s going to 0 of s time yc of s. So this one times s and s denominator simplifies. We are left with the limit of this thing over here. S goes to 0, s goes to 0, 0.5 divided 1 plus 1.5, which makes 1/3 and this is the limit of yc. If you want to know the steady state error, basically the error is the difference between the set point and the final value. So basically the set point is a step, so its limit is 1 minus the final value. You get basically 1 minus 1/3, 2/3. This as a function of c. As a function of p, so if we have a step in p, we need to compute y over p. Y over p, which means that at the numerator you will have the direct line from p to y, which is minus, right? You go through a minus 1 over s, and then at the denominator 1 plus l. So if you work it out, you get this, and again we are stable because both the criterion say so, and again you have the same denominator, no surprise as we expect. So let's use this transfer function over here to compute the final value of y of p, y due to p. So transfer function times 1 over s, you get this one, then final value theorem, multiply this guy times s and s simplify, then take the limit for s going to 0, all becomes 0, you're just left with minus 1 divided by 1.5, and this is also the error in modulus, because for p, if you have a p entering, then the error due to p, you can consider that c is 0, so basically you don't need to make 0 minus 2/3, you just get 0. You just get 2/3. So if we visualize the result by using MATLAB, basically for the set point, you can see the set point is this step over here. You get this line is y, and this is the difference between the two, the error, which goes as we forecast to 2/3, right? Yes, 2/3, as you can see. And for the step response to the disturbance, we get y going to minus 2/3, we said. And if you compute the error according to how you define it, will be the same value. Let's move on. Example 2. Now we consider this case, and pay attention, we have an integrator actually in the loop. So the integrator in the loop will probably, in the presence of input steps, either c or p, will probably yield some 0 steady state error, but just to be sure, we don't want to make any mistakes, we are going to compute it. So you can try and do it yourself, I recommend it, or you can wait for the solution in 3, 2, 1. So first thing to assess, is this thing stable in closed loop? Yes, it is. The reason is the same. We are still with the second order system, so the loop transfer function L, this times this, has 2 poles, so it goes to minus 180 degrees asymptotically, but never strikes it. So both the criterion in closed loop always stable. So no problem. Now we compute transfer function from c to y, so direct line at the denominator L divided by 1 plus L, which gives you this. So simplifying it, you get this one. Again, it is stable, all the coefficients have the same sign. So compute y of c as a function of c, multiply this times the Laplace transform of the step, then final value theorem. What we get? Well, we get this times s goes away, s goes to 0, you get 1. And then considering that the step is a unit step, the final value of the error, which is the final value of the set point minus the final value of yc, set point is 1 minus 1, you get in fact 0. So we have, as we could forecast, 0 steady state error due to set point. But on the other hand, let's check at the error, steady state error due to p. If we look at this one now, the transfer function is this one over here, and by doing the final value theorem, as you can follow over here, I will not go through the details now because it should be clear. You can always take the time, stop the video and read the details. You will see that actually we do not get 0, and this is actually what we expect, because if you remember what we said in the class, well, if you have a step in p, your steady state error will be 0 if the integrator is located here in what we call D1. D1 is just before P. So this integrator doesn't delete, let's say, the effect of the step over here, and that's why we have a non-zero steady state error. These are the pictures that show basically what it happens. You can take the time and look at them. I'm not going to comment. Anyway, you can just see that y goes to 1, so the error goes to 0 here, and no, instead here it stays non-zero. Third example. Solution in 3, 2, 1. Okay, this one is a bit more tricky concerning the stability because the system is order 3. And so L is order 3, and in order to check the stability we should actually do something more. So let's basically move to MATLAB. Let's move to MATLAB and do it here. So this I call it is the third example, so I call the loop transfer function of the third example is this one, which is a bit complicated, but I can apply both the criteria. So basically I'll draw both the diagram, and then I'll check whether both the criterion is satisfied. For example, if I hit minus 180 degrees for a negative gain, which seems to be the case over here. You see, we are below 0 over here. This is minus 180, below 0. So the closed loop system is stable. Now, reassured by this, we can continue the exercise and compute the transfer function from C to Y and from P to Y. So from C to Y again, this time I'll not describe the details. You can just stop the video or take the PDF of the slide and read it. Long story short, you get 1 for the limit of YC, which means that the steady state error is 0. Could we expect this? Yes, because there is an integrator here. You see, you can factorize an S over here. So if you factorize this S, then that means there is an integrator in the loop, integrator in L, so it cancels the effect of this guy over here, a step over here. And if what we learn in the class is true, then the integrator in this part should also destroy the effect, cancel the effect of the step over here, and then we compute from P to Y. Again, you can take the time to read the details. I'm not going to discuss it, it's just a calculation, but you can see that the effect of the perturbation of the disturbance P over on Y basically turns out to be 0. So basically you have a 0 effect at the limit due to a step of disturbance, which means 0 steady state error. And these are the plots if you care to have a look. Last but not least, this example over here again, which is the same box. We just the same boxes, let's say the same systems. We just care to look what happens if we have a ramp in P 1 over S squared. So solution in 3, 2, 1. The computation is exactly the same as in the last example, just a slight difference that now P, the Laplace transform of P, is 1 over S squared. So if you work it out, you can take the time and read it, you are left with a minus 1. So basically you get a non-zero steady state error, which is this one over here. You see, this is nice to look at because your P is a ramp and your Y is a constant, but it doesn't go to 0, so you will have a constant error at the limit. So to wrap it up, as you might have noticed in what we've seen in the beginning of the class, basically the number of integrators, increasing the number of integrators reduces the steady state error, and also if you look at the formulas, also increasing the gain K reduces the amount of the error in the cases in which your error is a finite number. you might want to go back and look at this formula, and you will see that k can actually reduce the error because it is at the denominator. If you have an error due to disturbance, due to that signal we call P, then what counts is the integrators found in the block D1, which means the integrator before the entry point of the disturbance. Remember that stability is a necessary condition. You have to check stability beforehand all the time, otherwise all of this doesn't make sense. And remember, every time you add an integrator in the loop, you add minus 90 degrees of phase. And remember, when the phase goes down, you have a risk of becoming unstable in closed loop. And anyway, be careful in drawing your conclusion. The best way to know the steady state value of a signal or of the error is to compute the transfer function, as we did in the example, multiply times the Laplace transform of the input, and after checking stability, use the final value theorem, and you will not make any mistakes. Just you have to be sure that you can compute limits properly. So, two final exercises for this class. This is found in the booklet. So we have this system over here in closed loop, which, if you got my explanation, you can straight away decide whether it is stable or not from R to Y. And the point here is to determine the gain K, which yields a zero steady state error. Pay attention between R and Y. It is not this the error. This is not Y, so it is something that is not shown. It's R minus Y for an input unit step. I strongly recommend you try and do it yourself. Otherwise, solution in 3, 2, 1. Well, the solution is here. I'm not going to detail the computation, but just say what you need to do. So the system in closed loop is stable because L is order 2, so never hits minus 180 degrees. Both the criterion, we are fine. What we need to do, we need to compute E as a function of R. So E is R minus Y, this arrow we care of, which I repeat is not shown here. You should just pull up an arrow here, pull up Y and make the difference, then this will be E. It is not this one, so E R minus Y. So E as a function of R, well, E is replaced by R minus Y, so basically it's R over R minus Y over R, which means 1 minus Y over R. Then you can compute this as 1 minus Y over R, usual transfer function in closed loop, so numerator K over S plus 2, denominator 1 plus L, because we are in negative feedback. You can work it out, you get this, then we have a step input, so R, the Laplace transform of R is 1 over S, so the signal we get as a result, as output, is Laplace transform of R times transfer function, which is this. Final value theorem for E, for the error, multiply this by S and takes the limit to 0, so S simplifies. We are left with this one, and we want it to be 0, right? So we want it to be 0, we just work out the computations and then we set this to 0, and this is 0 when 8 minus 2k equals 0, so it is 0 for k equal 4. That's it. Last example, last exercise. We have this closed loop over here. We want to compute the steady state error for a unit step of set point and for a unit ramp of disturbance. Okay, solution in 3, 2, 1. So first question, is this system stable in closed loop? Well, we have a problem here, kind of a problem here, because k is not given. So actually this system is order 3, so it will hit minus 180 degrees, and probably the stability depends on k, and we can actually look into that more properly by means of MATLAB, so I close the previous picture. So this loop transfer function is this formula over here, which features an integrator, by the way, and for k equal 1. Okay, I just replace k equal 1. So we can just draw the Bode plot of this one and apply the Bode criterion, and this will give us the answer if k equal 1, whether the system is stable in closed loop or not. Okay, let's look. When we hit minus 180 degrees, we are at minus 24 dB. So it means we are smaller than 0. So for k equal 1, we are actually closed loop stable. For which values of k can we be stable? Well, this curve over here has a gain margin by definition of minus 24 dB. Sorry, plus 24 dB. We can pull it up 24 dB before we strike 0 dB for minus 180. So, which means that we can increase the system of a factor of 24 dB, which is equivalent to 10 to the power 24 divided by 20, which is 15. So basically, for roughly k up to 15, the system is closed loop stable. If it is more than 15, it is unstable. So anyway, let's say k is smaller than 15, so we are stable in closed loop, and it makes sense to continue. So how do we compute the steady state error for a unit set point? Well, we just compute from r to the error, which is this one. F is 1, so it's like it's not there. So, or we just compute from r to y and then make the difference between the final value of I and the final value of the step. So let's do it from r to y. This is the transfer function, basically L divided 1 plus L. You can work it out and do the computation. Then, if I'm not wrong, of course, this is the Laplace transform of y due to the set point. Final value theorem yields 1, and so final error yields 0. And could we expect this? Yes, because we have an integrator in the loop in L. So we said an integrator in the loop is enough to cancel the effect of a step input in the set point. But we also said that it is not enough to cancel a step input in the it is also enough to cancel a step input in the disturbance because it is before the entry point. But now we have a ramp, so it should not be enough to cancel it, so we can expect something greater than 0 as a final value for y as a function of d. So we compute from d to y. You can work out the computation, etc., 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 and in fact we get a number that is, if I'm not wrong again, minus 1 over k. And as said, this is the case in which if you increase k, the error will be smaller in modulus, but as also we said before, increasing k too much might lead you to instability. And in fact, if you go beyond that value of 15 that we've seen before, you actually become unstable. So that's why you might think that tuning the controller is not easy. There is a kind of trade-off between stability and the precision. Adding integrators, increasing k, gives you more precision, but you get closer to the situation when you are stable. You lose robustness if you wish. You become less and less robust, and if you exaggerate, your system in closed loop turns unstable. So I think that's all for this class. It was rather dense, but a lot of examples that I hope you have taken the chance to try and do yourself. Now the next classes are focused on the problem of synthesis of controller. Basically, you have a set of specifications and you try to determine the controller. So basically the block over here, the D1, which gives you the specification that you desire. this block in order to get the specification that you desire. And now we know, for example, how to get the precision that we want, the static precision or dynamic precision with respect to certain given specified input signals. Okay, so that's all for today again, and thank you for listening, and everybody please stay safe.